Hello. We are rounding out Unit 4 with L'Hopital's rule, which is a shortcut to differentiation if you run into indeterminate form. This is so cool. We're going to look at a couple different cases: simple polynomials and powers, repeated use of L'Hopital's rule, trig functions and transcendental functions, and then some AP-style applications for L'Hopital. A bit of review. If you're given a limit problem, the first thing you do is try direct substitution. So we'll plug in -3 to the top, we get 0. Plug in -3 to the bottom, we get 0 again. And this is called indeterminate form. So what we've learned to do from here is maybe use some algebraic methods. Factor the top and the bottom, see if there's anything you can cancel out. Then try direct substitution again. When evaluating limits by direct substitution, there are 7 expressions known as indeterminate form. These expressions are 0 over 0, infinity over infinity, 0 times infinity, 1 to the infinity, 0 to the 0, infinity minus infinity, and infinity to the 0. We're going to focus on the first two. Consider the limit of the quotient, limit as x approaches c, of f of x over g of x. And if you get 0 over 0 or infinity over infinity, what we've learned so far is that you could try algebraic simplification, you could consider one-sided limits, or you can do magic. L'Hopital's rule is magic. And what it says is we have two functions, f and g, that are differentiable. So what we have is, let's say the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x is 0. Well, if you have f of x over g of x and you take the limit, that's the same thing as the limit as x approaches c of the derivative of f over the derivative of g. And that can make your life way easier. This also works for infinity over infinity or negative infinity over infinity. Just a couple notes. In order to use L'Hopital's rule on the AP Calculus exam, this is what you need to show. 1, explicitly show the limit of the numerator is 0, infinity, or negative infinity. Then do the same for the denominator. Then you can say, by L'Hopital's rule, okay, then write the original function, the limit as x approaches c, f of x over g of x, equals the limit as x approaches c, f prime of x over g prime of x. And then you can solve. So here's our first one. The limit as x approaches 5 of 2x squared minus 9x minus 5 over x minus 5. First thing we're going to do is try direct substitution. So if you plug 5 into the top, you get 0. If you plug 5 into the bottom, you get 0 again. So you want to show the numerator and you want to show the denominator both going to 0. And then it's nice to show this notation here. You're explicitly telling the reader, this is indeterminate form. Next, you say, I'm going to use L'Hopital's rule. And so to start that, you rewrite the original function. Limit as x approaches 5 of 2x squared minus 9x minus 5 all over x minus 5 equals, now we have another limit problem, the limit as x approaches 5 of the derivative of the top is 4x minus 9, and then the derivative of the bottom is 1. And now we try again. Plug in 5 to that, and it works. We get 11. Let's go again. The limit as x approaches -5 of the square root 4 minus x minus 3 over x plus 5. Always the first thing you do is direct substitution. If you plug -5 into the top, you get 0. We've checked the numerator. Now we have to check the denominator and show that if you plug in -5, you get 0 again. And then let's show the reader that we have indeterminate form. Now we tell the reader, I'm going to use L'Hopital's rule. So we rewrite the original function, and then we'll rewrite it again with the derivative of the top over the derivative of the bottom. But before we do, let's take the derivative of this over to the side here. I'm going to rewrite that as a fractional exponent. So the 1/2 comes forward, drop the power by 1. The -3 goes away. Where'd this -1 come from? That's the chain rule. We took the derivative of the outside. The derivative of the inside is -1. And then you can kind of rewrite it if you want to. That's the derivative of the top. The derivative of the bottom is just 1. So really, when we do a rewrite of this, it's the limit as x approaches -5 of f prime of x, and that's fine to leave it like that. And then we can plug in -5, and we're done, -1/6. Sometimes once isn't enough, but lucky for us, we can do L'Hopital's rule once, twice, 3 times, as many times as it takes to get to an actual limit. So here we have the limit as x approaches -infinity, x squared over e to the -x. All right, we'll start with the top. Limit as x approaches -infinity of x squared is infinity. The limit as x approaches -infinity of e to the -x is also infinity. So we do have indeterminate form, this time of infinity over infinity. Well, that's okay. We can use L'Hopital's rule, and we will rewrite the original function. Still using limit notation, we'll take the derivative of the top and put it over the derivative of the bottom. So x squared goes to 2x, e to the -x goes to -e to the -x. And please make sure you are rewriting that limit notation. Now let's try again. So we'll take the limit as x approaches -infinity of 2x, and we got -infinity. Let's try the bottom. The limit as x approaches -infinity of -e to the -x is also -infinity, and we have another indeterminate form. That's okay. Let's try again. We don't have to rewrite this whole string, just this one. So the limit as x approaches -infinity of 2x over -e to the -x is, writing our limit notation again, derivative of the top over the derivative of the bottom. And now when we plug in -infinity, we get an answer. Example 4 is a large polynomial on top and a large polynomial on the bottom. And while polynomials are pretty easy to take derivatives, that's just a lot of writing. So let's do this. I'm going to say that this equals the limit as x approaches -2 of f of x over g of x. So the numerator now has a name of f of x, and the denominator now has the name of g of x. And that'll make this go a little bit faster. First, we're going to plug in -2 to the top. And look at, I just wrote f of x. The limit as x approaches -2 equals 0. Let's try the denominator. The limit as x approaches -2 of g of x also equals 0. And there we have our indeterminate form. So we bring in L'Hopital. And when we rewrite the original problem, we can just use our f of x, g of x notation. But then we actually have to show the derivative. So the limit as x approaches -2, here's the derivative of the top over the derivative of the bottom. Now, are we done? Well, if we plug in -2 to the top, we get 0 again. But notice I used f prime here. The limit as x approaches -2 of f prime equals 0. And the limit as x approaches -2 of g prime is 0. So we've saved a lot of writing. Once again, we have indeterminate form, and we're going to give this one more go. By L'Hopital's rule, the limit as x approaches -2 of f prime of x over g prime of x, and now let's take the derivative of the top and the derivative of the bottom. And try plugging in -2 again, and this time it works, -5 over 2. We can do the same thing with trig functions and transcendental functions. So here we have the limit as x approaches 0 of sine of x times 1 minus cosine x all over x squared. Same process, even though there's trig functions. Plug in 0 to the numerator. You got 0. Plug in 0 to the denominator, you get 0 again, and we have indeterminate form. Okay, bring in L'Hopital. Now, if you'd like to take the derivative of the top and take the derivative of the bottom, you're more than welcome to do that. I want to show you just a different approach to this. I'm going to break up this original problem into two functions being multiplied together. And I can do that with the properties of limits. And it's just easier to take the derivative of the top and the derivative of the bottom of those separately. So the derivative of sine x is cosine, derivative of x is 1, derivative of negative cosine is sine, derivative of x is 1. See, that's just super pretty. Now we can plug in 0. So cosine of 0 is 1, sine of 0 is 0, so we have an answer of 0. One other approach to this problem might be to recognize special limits. So when I broke that original function into two functions being multiplied together, did you notice these special limits that we learned a couple units ago? The limit as x approaches 0 of sine x over x, that's 1. The limit as x approaches 0 of 1 minus cosine x over x is 0. And we got to the same answer without even touching L'Hopital's rule. Either approach is completely legit. Oh good, natural logs and e to the x. The limit as x approaches 1 of ln of x minus x plus 1 over e to the x minus e. Step 1, plug 1 into the top. Ln of 1 is 0, minus 1 plus 1. Yep, that's 0. And then plug in 1 to the bottom. You get e minus e, so that's another 0. We have our indeterminate form. So we bring in L'Hopital, rewrite the original function, and then take the derivative of the top over the derivative of the bottom, keeping our limit notation. Remember, the derivative of ln x is 1 over x, and then the derivative of negative x is negative 1. E is a constant, so that just falls off, and the derivative of e to the x is e to the x. Now use direct substitution. If you plug in 1 to the top, we get 0, but if you plug in 1 on the bottom, you get e. So it's not indeterminate form, it's 0 over e, so that's 0. Okay, some AP style problems. The table below gives values of a twice differentiable function y equals f of x. Use the table to find the limit, if it exists, and justify your answer. All right, so the limit as x approaches -2, f of 3x plus 2 over x squared minus 4. Well, if we start with direct substitution and plug in a -2 up here, we get f of 3 times -2 is -6, plus 2 is -4. And then -2 times -2 is 4, minus 4 equals 0. Well, what's f of -4? Oh, 0. All right, so the limit as x approaches -2 of the top is 0. The limit as x approaches -2 of the bottom is 0. So we have indeterminate form. So here comes L'Hopital. Rewrite the original function. And then when you take the derivative of the top, you use the chain rule. So here's the derivative of the outside, keeping the inside the same. And then the derivative of 3x plus 2 is 3. And of course, the derivative of x squared is 2x. And now let's try direct substitution by plugging in -2. So this time we get f prime of -4 over -4. Oh, don't forget the 3 on top. And f prime of -4 is 8. So it looks like we have 24 over -4 is 6. Oh, now we have a graph problem. Use the graph of y equals g of x, shown below, to find the following limit, if possible. Use proper notation to justify your findings. The limit as x approaches 3, g of x over x minus 3. Well, let's plug in 3. What's g of 3? G of 3 is 2. Okay. What's 3 minus 3? 0. So we have 2 over 0. That's not indeterminate form. That's just a non-existent limit. So L'Hopital's rule doesn't even apply here. Last one, example 9. The differential equation for the curve y equals h of f is given by dy dx equals 3x over y plus 2. Given that h is twice differentiable and h of 3 equals -1, find the limit as x approaches 3 of h of x plus x minus 2 over ln 7 minus 2x. Wow. Before we begin, I just want to tell you, look at this dy dx. That's going to come in handy in a little bit. That's actually h prime of x. So watch for that. All right, starting by direct substitution, the limit as x approaches 3, h of x plus x minus 2. Well, they told us that h of 3 is -1, so we get -1 plus 3 minus 2, which is 0. And then on the bottom, 7 minus 2 times 3, so that's 7 minus 6. The ln of 1 is 0. So we do have our indeterminate form, and we can utilize L'Hopital's rule. So rewrite the function. When we take the derivative of the top, h is just going to become h prime, and then x will be a 1. And then the bottom, let me just do that over here for a second. So if we're taking the derivative of ln of 7 minus 2x, we are going to use the chain rule. So the derivative of ln is 1 over x, but we're going to do 1 over, keep the bottom the same, okay, times the derivative of the inside, which is -2. Now, h prime of x. Come back up here. That's when I told you that we were going to use dy dx. So h prime of x, we're going to plug in this point that they gave us, 3, -1. 3 times 3 over -1 plus 2, that's 9. So now we have 9 plus 1 on the top, and then plug in 3 to the bottom, -2 over 7 minus 6, 10 over -2, which is -5. I like L'Hopital. It's a cool shortcut, but it doesn't mean there's no work involved. All right, that's the end of Unit 4. I'll see you again in Unit 5.